All right, so now we're going to look at some problems looking at net force. So remember that you will have objects and it's not always going to be just one force acting on that object. Sometimes you will have more than one force, and in order to calculate, let's say, acceleration of the object or the mass of the object, you might need to look for the net force. So you need to account for all the forces that are occurring on that object. So when you have two forces, you will add them when they are working together. So, oops, you're going to add them when they're working together. So basically, if they are in the same direction, you add them. If they are in opposite directions, you subtract them. So this is for same direction, you will add them. And then you will subtract them when they are opposing each other or they are going in different directions. Okay. So let's look at a problem. Arnold needs to lift a 35 kilogram rock. If he exerts an upward force of 502 newtons on the rock, what is the rock's acceleration? So we know that the rock is accelerating. We know it's going up. So what I suggest we do is let's draw a diagram first. Here's our rock. We know that Arnold is applying a force going up of 502 newtons. But I also know, because I'm moving up and down, I really need to think about the weight of the object. So the force due to gravity. And I do not know what that is at this moment. But anytime that we have something that's moving up or down, account for your weight or your force due to gravity. So in this case, the rock is moving up, so we need to account for the weight. So the rock is not experiencing 502 newtons. We need to know what the net force is to actually get the rock's acceleration. So we're looking for the rock's acceleration here, and it's not going to be 9.8. We are not looking at free fall here. So we need to figure out the acceleration going up. Okay. And in order to do that, I need to know what the net force of the object is. So I need to know how much force is the rock actually experiencing, because we have an applied force of 502 newtons, but we also have a force that's bringing it down. So they're fighting each other, they are opposing each other. So it's not experiencing 502 newtons of force. That's not the total force. We need to account for the weight here. So we need to get F of G. We need to get that. We know that the force due to gravity is equal to mass times acceleration, and we know in this case it's a special acceleration of 9.8. We also know that the mass of the rock is 35 kilograms. Okay. So I can solve for F of G here. F of G is equal to the mass, which is 35, times acceleration due to gravity, which is 9.8. So force due to gravity is 35 times 9.8. Which is 343 newtons. So the rock is experiencing 343 newtons of force going downwards, while it's also experiencing 502 newtons of force going up. So to get the net force, since they're going in opposite directions, I will subtract them. So it's 502 minus 343. 159 newtons of force. That is the net force being experienced on the rock. So now I can solve for the acceleration that is going up. So force is equal to mass times acceleration. The net force is 159. The mass is 35. So now I can solve for acceleration. Okay, so 4.5 meters per second squared. Okay, so this is my acceleration of the rock, and that's the acceleration going up on the rock. So because we're looking at up and down movement, we're going to account for force of gravity. So we need to look at both the forces being applied here. So the force of gravity, or the weight, and also the force that Arnold applies on the rock. So let's do another example of net force. Okay, so Annie is holding a stuffed dog with a mass of 0.3 kilograms. When Sarah decides she wants it, she tries to pull it away. If Sarah pulls horizontally on the dog with a force of 10 newtons, and Annie pulls with a horizontal force of 11 newtons, what is the horizontal acceleration of the dog? So first of all, we are looking for the horizontal acceleration of the dog. It tells us that the mass of the dog is 0.30 kilograms. And then we also know that we have two forces being applied here. We have a force that Sarah's applying, and then we also have a force that Annie is applying. Annie applies a force of 11 newtons, and then Sarah applies a force of 10 newtons. So let's draw a diagram of this. We have a dog, and Annie is pulling the dog with 11 newtons of force, and Sarah is pulling the dog with 10 newtons of force. So we need to know the net force on the dog. Because we're moving in opposite directions, we're going to subtract. So 11 newtons minus 10, and the net force is actually 1 newton towards Annie. So the net force is 1 newton. And I know that force is equal to mass times acceleration. I have a mass of 0.3. And then I also know the net force is 1. So 1 is equal to my mass of 0.3 times my acceleration. So now to solve for acceleration, I divide both sides by 0.3. And I get 3.3 meters per second squared. All right, so with this problem, I think it was a little bit easier to see that you had two forces because it's talking about two people fighting over the dog, and it gives the amount for the forces. We don't actually need to worry about the force of gravity here because it's just a horizontal motion. The tension between the two girls is going to be enough to overcome the force of gravity, so it's not going to fall. So we don't need to worry about that. We're going to account for the force of gravity when objects are moving up and down, so not from side to side. All right, so let's go ahead and look at one more type of problem that you're going to see. So this one is not in your notes, but I'm going to do it anyway because it's important, because it goes over an important concept. So a student raises their 15-kilogram backpack from the floor at a constant velocity of 5 meters per second. How much force must the student apply? So right here, we're looking for force. Okay, and really we want to know how much force the student is going to apply. We're not looking for net force here. We're looking for an applied force because it tells us the student must apply this force. That's what we're really looking for. That's the specific force. It also tells you that a mass is 15 kilograms. And we know that the backpack is going up. So really what we have here is we have an object that is moving up. We're looking for the force applied here. And we know that there is going to be a force of gravity here also. However, it tells us something important. It says constant velocity. Anytime that we have a constant velocity, we know something. we know that the acceleration then is 0. So we know the acceleration on this book bag is 0 because it tells us that we have a constant velocity. So if A is equal to 0, then and you know force is equal to mass times acceleration. So force is equal to whatever the mass is, doesn't really matter, times 0. Any number times 0 is going to give you 0. Okay, so really what this means is that the net force on this book bag is 0. So I told you there's going to be two cases where you're going to have net force equal 0. One is the object is not moving. The other one is where you have a constant velocity. So your net force here is 0. So I'm looking at this diagram right here, and I know I have a force applied going up, I have a force of gravity going down, but I know that my net force is 0. Well, I know that since I've got opposing forces here, that my force applied minus my force of gravity is equal to my net force because they're opposing each other. Now I know my net force is 0, so let's go ahead and substitute in. So if I solve this for, let's say, f of g, so I add f of g to both sides, what this is saying is that the force of gravity is equal to force applied. So let me just simplify what I said here, or what we just did here, all this stuff. Because we're moving at a constant velocity, acceleration is 0. Since the acceleration is 0, the net force is 0. That means that your force of gravity is equal to your force applied. They are equal to each other because we're moving at a constant velocity. So to simplify it, if you have an object moving at a constant velocity, if you have two opposing forces, they will be equal to each other. So instead of subtracting, you are going to actually just set them equal to each other. All right, so we know the mass is 15 kilograms. We know that the force of gravity is going to be equal to the force applied. So we know this. So that means we can solve for force of gravity, and that's equal to the force that the student applies. All right, so let's solve this. So force of gravity is equal to mass times acceleration. We know the acceleration in this case is going to be 9.8 meters per second squared. So force of gravity is equal to 15 times 9.8. So the force of gravity is equal to 147 newtons. And we know because we're moving at a constant velocity, the forces that are opposing each other are equal. So the force that the student must apply to maintain a constant velocity should be 147 newtons. All right, so this is a special case here. Anytime that you see constant velocity, if you have two forces that are opposing each other, they're equal to each other. All right. We're going to look at some different types of problems in the next video, but I hope you guys found this helpful. All right, see you in class. Okay, so let's do this problem. if you hold a 1-pound object using 6.5 newtons of upward force, what is the net force on that object? And then right here it also tells you that 1 pound is equal to this many kilograms. So for this problem we're going to have to do probably some conversions and a little bit more thinking. Okay, so let's go ahead and draw a diagram really quick. Okay, so we're holding this 1 pound object, and so let's just say it's this, okay, and the object is going up. We know that the object is going up. We also know that the force applied is equal to 6.5 newtons, because that's what the upward force is. Now, we know that this cannot be the only force that this object experiences, because if we have up and down movement, we need to account for the weight. We need to account for the force due to gravity. Okay, so we have two forces here. We have the force of gravity, and then we also have the force applied going up. And we know that this object is going to be moving up, so the force applied has to be greater than the force of gravity. So first of all, let's go ahead and figure out what the force of gravity is. Okay, so force of gravity is equal, well, any force is equal to mass times acceleration. Okay, but this is a specific force, it's gravity. So the acceleration should be equal to the acceleration due to gravity. Well, acceleration due to gravity is 9.8 meters per second squared. Okay, so we know it's going to be 9.8 meters per second squared because it's the force due to gravity. It's a special kind of force, so we actually know the acceleration. Acceleration due to gravity is 9.8. So we have that. So to get the force of gravity going down, really what we're solving for is the weight. We need to get the mass. Well, we know that it weighs 1 pound, but we know we can convert that to kilograms. So let's go ahead and do that. The object is 1 pound. We know that 1 pound is equal to 0.45 kilograms. So pounds goes on the bottom, kilograms goes on the top. 1 pound is equal to 0.454 kilograms. So really we have mass of 0.45 kilograms. Didn't even really need to do the math for that. So I have mass, which is equal to this. All right. And we know the acceleration is 9.8 because this is the special force of gravity here. All right, so force of gravity is equal to mass, 0.454, times 9.8. So less than 5 almost. All right, so 4.44 is my force due to gravity. Newtons. Okay, so the reason we're doing this is because it wants to know what the net force is. So anytime that we're looking for net force, we need to figure out what all the forces that are acting on this object are. So we know that the force due to gravity is equal to 4.44 newtons. We know that the force going up is this, and because they're going in opposite directions, you're going to subtract. So 6.5 minus 4.44 is 206. So that is a net force acting on this object. So anytime that you have objects that are moving up or down, you need to account for the weight, so the force due to gravity, in your problem. You need to look at the force due to gravity. All right, this was a little bit trickier, especially because we haven't talked about weight yet. So this is a good problem to have if you are confused about weight and objects moving up and down.